In this lesson, we are going to look at the purpose and operation of the turn indicator, and also the slip indicator. Later in the lesson, we will also look at a development of the turn indicator known as the turn coordinator. The slip indicator is often incorporated in the instrument face of the turn indicator or the turn coordinator. Bear in mind, however, that the slip indicator is a separate instrument which functions independently from the turn indicator or the turn coordinator. The turn indicator, which is part of the instrument face highlighted here, uses a rate gyro to measure the rate of turn around the aircraft's vertical axis. The slip indicator is a simple pendulous device which indicates whether a turn is balanced or not. We will look at both instruments in some detail, starting with the turn indicator. The turn indicator uses a rate gyro aligned to the aircraft's horizontal axis. The rate gyro has only one gimbal, therefore classed as having only 1 degree of freedom. The way it works is that if the aircraft banks without turning, the gyro axis has the freedom to remain horizontal in its gimbal. However, if the aircraft turns or yaws, in this case to the left, the frame, which is attached to the aircraft, turns with it. The gyro rotor will be subjected to a primary torque around the ZZ axis, where the gimbal meets the frame, here and here. This torque will be precessed 90 degrees in the direction of rotation, which, in this example, is with the top of the rotor coming down towards the pilot. The resultant precession will cause the gyro to tilt around the YY axis. As the rotor tilts, it causes a spring between the gimbal and the frame to be extended. The resulting spring tension subjects the frame to a secondary torque acting around the YY axis. This secondary torque is also precessed through 90 degrees in the direction of rotor spin to produce a secondary precession in the same direction as the aircraft is turning. Eventually, the spring torque will reach a value where it is producing a secondary precession equal to the rate of turn of the aircraft and in the same direction. When this state is reached, the gyro will be precessing about the vertical axis at the same rate as it is being turned, because it is attached to the aircraft and frame, and no further torque will be applied by the turning. This gives us a spring tension which is proportional to the rate of turn of the aircraft. By a suitable design choice of spring tension, the angle of tilt can therefore be calibrated to indicate a rate of turn at a specific TAS, and a pointer linked to the gimbal can be used to indicate the amount of tilt on a graduated scale on the face of the instrument. The rate gyro may be air-driven or electrically driven. In the electrically powered instrument, a red warning flag or off sign on the face of the instrument will indicate if the power to the instrument has failed. The rotor RPM is low compared to the DGI and artificial horizon rotor speeds because the turn indicator uses the gyroscopic property of precession to measure rate of turn. Lower spin speed means less gyroscopic rigidity, giving greater precession, so a high rotor speed is not required. If the gyro spin speed slows, which may happen in an air-driven gyro should the air filter become partially blocked or a leak develops, the gyro will underspeed, and the instrument will underread the rate of turn. The reason that the gyro underreads is that if the gyro spin rate slows down, rigidity reduces. However, the secondary precession must always be equal to the actual rate of turn craft. If rigidity reduces, then the secondary torque from the spring tension must also reduce in order to maintain the same precession. If the instrument is under reading, what would appear to be the correct indication on the instrument face would, in fact, result from the aircraft turning faster than the indicated rate of turn, and the aircraft will complete the turn sooner. We can say, therefore, that an underspeed will cause an underread and an under-time turn. On the other hand, if the gyro overspeeds, the opposite will apply, and the instrument will overread the rate of turn. Therefore, the actual rate of turn will be less than indicated. So an overspeed will cause an overread and an overtime turn.
A properly executed turn will be a balanced turn where the angle of bank is correct for the true airspeed and rate of turn. The slip indicator gives a direct indication of the state of balance of the turn. The most common version of the slip indicator consists of a solid ball in a liquid-filled, curved, transparent tube. The liquid in the tube damps out any unwanted oscillations of the ball. In straight and balanced flight, gravity will keep the ball centralized in the lowest part of the tube between the two etched lines. In turn, the ball will be subject to an additional or centrifugal force, which we will call C. The magnitude of the centrifugal force experienced will be proportional to the true airspeed and the rate of turn. The ball will be displaced by this force and will come to rest in the tube when the centrifugal force acting on the ball equals the resultant weight of the ball. Diagrammatically, this is illustrated here. This is a balanced turn, and in a balanced turn, the resultant of the force of gravity and centrifugal force will lie in the aircraft vertical plane, and the ball will remain centralized in the tube. However, let's look at a situation now where a turn has been initiated, but the angle of bank applied is insufficient for the rate of turn. The turn will be unbalanced, and the ball will be displaced away from the aircraft vertical towards the outside of the turn. With insufficient bank, the aircraft will skid out of the turn, and the indication on the slip indicator will be that the ball will have moved in the opposite direction to the turn. However, if we assume that the TAS and the rate of turn has remained the same as for the balanced turn, the force of gravity and centrifugal force experienced will not have changed either. What has happened is that the tube, and therefore the aircraft, has moved relative to the ball. We can say, therefore, that a skidding turn results from too little bank, and the ball in the slip indicator will appear to move in the opposite direction to the turn. Let us suppose now that the angle of bank is too great for the rate of turn. The aircraft will slip into the turn, and the indication on the slip indicator will be that the ball has been displaced away from the aircraft vertical, this time towards the center of the turn. We can say, therefore, that a slipping turn results from too much bank, and the ball will appear to move in the same direction as the turn. Having now looked at the principle of the turn indicator and also the slip indicator, let's put the two together and see what indications we might expect to see on the turn and slip indicator. A balanced turn to the right. Note the ball is centralized. A balanced turn to the left. Here we have a left turn and insufficient bank has been applied for the rate of turn. The aircraft is skidding outwards in the turn. Similarly, the aircraft is now skidding outwards in a right-hand turn. This example, too much bank has been applied for the rate of turn, and the aircraft is now slipping inwards in a right turn. And the last example shows us a situation where too much bank has been applied for the rate of turn, and the aircraft is slipping inwards in a left-hand turn. The turn coordinator is a development of the turn and slip indicator. This is what the instrument looks like. From the constructional point of view, the difference between the turn and slip indicator and the turn coordinator is that the rate gyro axis in the turn coordinator is inclined to the fore and aft axis of the aircraft by approximately 30 degrees. This makes the gyro sensitive to aircraft roll or bank, as well as to yaw or turn. An actuating pin and claw mechanism transmits the precession movement of the gyro to the aircraft wing symbol on the face of the instrument. The principle of operation is much the same as the turn indicator, but because the turn coordinator is sensitive to bank as well as to yaw, it responds quickly to the initiation and completion of a turn and to any change in the rate of turn. Looking at the example of a typical instrument display shown here, we can see that the slip indicator is the same as the one incorporated into the face of the turn indicator. However, we can also see that instead of a needle pointer, the indicator used is an aircraft wing symbol. And in the example shown here, this particular instrument is calibrated for a rate 1 turn only, that is, a turn of 360 degrees in 2 minutes. Make a note of this, because the instrument illustrated here is accurate only for this rate of turn. A midpoint rate of turn cannot be interpolated. In a normal banked turn, the aircraft symbol tips in the direction of the turn, and by keeping the aircraft symbol aligned with the specific marker, and by also keeping the ball in the center of the slip indicator, a balanced rate 1 turn will be achieved. Make a note, however, that the aircraft symbol does not indicate the bank angle, but only the direction and rate of turn, and it is not to be confused with the artificial horizon, which it can resemble in appearance. To conclude the lesson, let's look at some straightforward calculations which might be encountered. To start with, let's work out the diameter of a turn flown at rate 1 at a true airspeed of 360 knots. By now, we should have noted that a rate 1 turn is a turn through 360 degrees in 2 minutes, or a turn of 3 degrees per second. Rate 1 turns are regularly used in instrument flight. So, returning to our calculation, we now know it will take 2 minutes at a true airspeed of 360 knots to complete the turn. At 360 knots, the aircraft is travelling at 6 nautical miles per minute. So the total distance travelled in 2 minutes will be 12 nautical miles. The circumference of the circle the aircraft has flown is therefore 12 nautical miles. We can find the value of a circle circumference by using the formula pi times the circle diameter, or pi d. Therefore, 12 nautical miles equals pi times the circle diameter. Or, rearranging the formula another way, the circle diameter equals 12 divided by pi. For the purpose of the calculation, we can take the value of pi to be 3.142. So 12 divided by pi gives us the answer to the question, which will be that the diameter of the turn is 3.8 nautical miles. We can also get an approximate answer to the same question using a quick rule of thumb method, where the diameter of the circle flown at rate 1 equals the true airspeed divided by 100. In this case, the answer to the same question would be 3.6 nautical miles. Another rule of thumb formula, which has a very practical use, gives us the required angle of bank for a rate 1 turn at any given true airspeed. The rule of thumb formula is the angle of bank equals the true airspeed divided by 10 plus 7. So let's assume the true airspeed is 120 knots, and let's apply the rule of thumb formula. Angle of bank equals 120 divided by 10 plus 7, which is 19. 19 degrees is therefore the required angle of bank for a balanced rate 1 turn at 120 knots. This concludes the lesson on the turn and slip indicator. A brief summary of the main points of the lesson follows. The turn indicator uses a rate gyro to measure the rate of turn around the vertical axis. The turn indicator uses a horizontal axis rate gyro. The turn indicator has only one gimbal and is classed as having 1 degree of freedom. The slip indicator gives a direct indication of the state of balance of the turn. In an air-driven gyro, a partially blocked air filter or a leak will cause the gyro to underspeed, and the instrument will underread the rate of turn, and the turn will be under time. If the gyro overspeeds, the instrument will overread, and the rate of turn and the turn will be over time. The rotor RPM is low compared to the DGI and artificial horizon because the turn indicator uses the gyroscopic property of precession to measure rate of turn. Lower spin speed means less gyroscopic rigidity, giving greater precession. In an electrically powered instrument, a red warning flag or off sign will indicate the power to the instrument has failed. The instrument indications of a balanced, skidding and slipping turn should be noted. A skidding turn results from insufficient bank, and the ball will appear to move in the opposite direction to the turn. A slipping turn results from too much bank, and the ball will appear to move in the same direction as the turn. In the turn coordinator, the rate gyro axis is inclined to the aircraft's fore and aft axis by 30 degrees. In the turn coordinator, the inclination of the gyro axis makes the gyro sensitive to roll or bank as well as to yaw or turn. A rate 1 turn is 360 degrees in 2 minutes. A rule of thumb formula to calculate the diameter of a turn flown at rate 1 is TAS divided by 100. A rule of thumb formula to calculate the required angle of bank for a rate 1 turn at a given true airspeed is TAS divided by 10 plus 7.